I'm Eiji Ohtani from Tohoku University. First of all, thank you, Barbara and Alex, for inviting me this very exciting and stimulating workshop. I learned a lot during 2 days. And thank you for scheduling the last of this symposium. And it a bit hard to wait until the end of this workshop. Today, I'd like to talk about the hydrophases in transition zone on top of the lower mantle. And I'd like to talk about some relation to the seismicity. I'd like to talk about the hydration and the formation of hydrophases and the hydration of such hydrophases in the transition zone on top of the lower mantle. And this is the first talk. And the second talk is a metastable olivine wedge. Some people say that this is a signature of dry subduction. I'd like to talk about the effect of water on this metastable olivine wedge. And third topic is the transformation of hydrogen further into the lower mantle. So my talk is essentially these three topics. This is sort of system, and the Earth is here. And snow line is between the Mars and Jupiter, so that it is strange that the water exists in the Earth. However, we have water ocean, and also that this ocean might be provided by the comet or chondritic materials in later stages. And also these volatile materials circulate, subduct into the deep mantle and stagnate, partially dehydrate and stagnant, and further collapse into the core mantle boundary. So that volatile circulation is quite important issues. And also the effect of water in various phenomena, including seismicity, is one of the outstanding problems. This is subduction zone tomography of the subduction zone of circum-Pacific regions. Central Japan, Central Africa, America, and Indonesia is born in, and Tonga. We can see subducting sloughs in the mantle transition zone and lower mantle. However, as you know, the deep earthquake is up to the top of the lower mantle, and there is deep earthquakes in the transition zone and on top of the lower mantle. This is a recent study of the deep earthquake in Tonga. It's very deep, around 700 kilometer depth. This is also summarizing that the event of the deep earthquakes of the various subduction zones. And we clearly see is that these deep earthquakes in many subduction zones except Europe. So that deep earthquake are remarkable characteristic of slabs. And there are several mechanisms in these 2 days. There is several discussions about the existence of metastable olivine wedge, which could be originated by the alpha-beta transformation kinetically. And this could be a signature of dry, because dry conditions, transformation occur very sluggishly. So that this is a point which I want to address today. And also the hydration of hydrophases. And the hydration and fluid formation could be one of the important processes to generate deep earthquakes, like upper intermediate earthquakes. So that this is very interesting hypothesis. And there might be some other hypotheses like carbonate, magnesite, or some melting. So that there are several mechanisms for formation of deep earthquakes. First, I would like to address about the dehydration at the transition zone and the lower mantle, and which are related to some seismicity. As Carmen already shows that this is mineral assemblage in the upper mantle transition zone and the lower mantle. And water storage capacity in the mantle transition zone is very high. Beta phase contains up to 3 weight% of water, and gamma phase, the ringudite contain up to 1.5 or 2 weight% of water. So that transition zone is a storage place of a huge amount of water. On the other hand, the lower mantle, upper mantle, lower mantle relatively dry. And this observation is supported by several high-pressure minerals observed in kimberlite, diamond in kimberlite. This is a phase egg. This is hydrophases, and also phase delta. This is observed in as inclusions in diamond from Brazil. And also, the Pearson observed hydrous ringudite. And this contains about 1 weight%, which is as inclusions in diamond from Brazil kimberlite. So that these observations suggest that some part of the transition zone is actually wet. And there is the water carrier in the mantle transition zone, as already a previous speaker suggested that the phase A was at ringudite, phase E, phase D, superhydrous phase B, and phase egg. So these are important hydrous minerals in the transition zone. And important point is hydrogen partitioning between these hydrous minerals and the wozriate and ringudite. So important point which I want to address is this point. This is phase relation of existing minerals, pressure and temperature. And this shaded area is mantle transition zone. As you know, in general, the wozriate and ringudite can contain large amount of water. But at lower temperature during subduction geotherm, of course, wozriate and phase E exist. If you go further deep, ringudite and superhydrous phase B exist. So this is very important signature. So there is a coexistence of wozriate and phase E, and ringudite and super B. How about the partitioning of hydrogen? That is a very important point, and many people ignore it. Here is mineral assemblage in the along the slab geotherm, and so clearly observed we can see the coexistence of borybine and hydrous phase AE, wozriate and phase E, and ringudite and super B. So that how behave hydrogen? And the conclusion is that hydrogen-like hydrous phases. Here, this is very interesting phase relation. And if this is very simple experiment, if you can put ringudite and 5% water and place at very high pressure, 20 GPa, and low temperature, ringudite disappears. The stable phase is illuminized, super B, and stishovite. If you want to put more water, 11% of water, always ringudite disappears. And super B and D is stable phase. So this is some dynamic stability. And hydrous ringudite is not stable compared to the hydrous phases. That is some dynamic existence of this simple phase relationship. So this indicates that most of water can be absorbed by these hydrous minerals. And essentially, ringudite and wozriate is could become dry even under the wet conditions because of the existence of hydrous phases. So this is a very important point which I want to address today. And this is clarifies the water content with temperature at fixed pressure range. So water content in wotherite decreases with increasing temperature. So that with warming up of the slabs, dehydration could occur because solubility decreases with temperature. But if you go very low temperature, wotherite and phase E is stable. And partitioning of hydrogen moved to phase E, so that essentially wotherite could be very dry. We need to check real measurement, but this is simple thermodynamic calculations, estimations. So that if you go higher temperature, dehydration of phase E produces fluid. So dehydration, then some amount of fluid can absorb to the wotherite. And also, wotherite dehydrate at higher temperature. So this is very important information about the water content in transition zone minerals. So that this is the pressure and temperature. We can see the choke point here, and the dehydration tends to occur here. But cold subduction phase is stable. And if you go further, high temperature, phase E decomposes. And wotherite contains a large amount of water, but with increasing temperature, dehydration reaction occurs in wotherite in the upper part of the transition zone. The similar situation occurs in ringotite at the bottom of the lower part of the transition zone. Super B is stable, but if you go higher pressure, the composition of super B dehydrate, and some amount of water can be trapped in ringotite. So this is a very interesting situation in dehydration processes in the mantle transition zone. And also that base of the transition zone is an interesting place because dehydration temperature is very low. This is the dehydration of phase D and super B, we can see here. And our experiments show that most of the hydrogen can be dehydrated relatively low temperature. And so this is also a relative low temperature hydration point, so could be second choke point for the hydration. And if you go higher pressure and high temperature, we can see coexistence of delta phase, which is very interesting hydrous minerals, stable under the lower mantle condition. I will address these issues later. So that there is some anomalous region at the top of the lower mantle, which show lower seismic velocity, could be some dehydration processes. And this is by Karato and dehydration or partial melting, but dehydration could be more likely. During the warming up of the slab, a dehydration reaction could occur at the bottom of the lower mantle. So that this is several dehydration sites exist in the transition zone. And dehydration of phase E, super B, and phase D with increasing temperature. So this is one point. And further, if you go higher temperature, hydrous wotherite and hydrous ringotite could be formed. So that, but with increasing temperature, solubility decreases. So that further high temperature, increase of temperature could produce dehydration. And third point is base of the mantle transition zone. The composition, the composition of phase D and super B at the top of the mantle could occur. So that there will be three important points of the hydration in the mantle transition zone. And the hydration can trigger the deep seismicity. And this reaction have delta V is negative. Let's move on to the next talk, which is metastable olivine wedge. And I'd like to address about the effect of water on this metastable transition kinetics. And simple-minded people also consider that existence of metastable olivine wedge is a signature of dry conditions. And we would like to consider, check about that possibility. So that this is a pattern, this is a cartoon of the subducting slab. And this is olivine stable regions and beta phase and gamma phase. Under the dry conditions, metastable which could exist. And under the wet conditions, the action is accelerated by the water, and there should be no metastable olivine wedge. So that this could be a signature of dry and wet. And there is some observation that in case of Tonga, there is no metastable olivine wedge, and observed for 10-kilometer discontinuity in the slab. So that this looks like might be wet. But in Japan, some Kawakatsu reported the metastable olivine wedge in southwest Japan. And also recently, Jing and Dappenzout group observed this metastable wedge, olivine wedge in Western Pacific slabs. So that in Japan, Japanese subduction, they reported this kind of metastable olivine wedge. So that let's consider about the effect of water on the signature of this kind of reaction kinetics. So this is experimental work. If you put some olivine crystals, olivine cubes, and place under the dry conditions at high pressure and high temperature, about 13.5 GPa and about 1,000 degrees C, eventually the reaction stops. It takes a long time. This is time and a fraction of transformation. If you put small amount of water, transformation occurs quickly. This is a qualitative experiment. But we can do more precisely by using in situ X-ray diffraction and to check the to study the kinetics of this phase transformation kinetics. So this is the time, and this is a fraction, volume fraction of Woodleyite. So this is dry and low temperature, high temperature, and this is also the wet conditions. Wet condition accelerates transformations, and high pressure, high temperature, and wet condition, the reaction completes almost in about 500 minutes. So that we can analyze the effect of water like that. So this is a dry, this is gross velocity of Woodleyite, alpha beta transformation, and the growth rate of Woodleyite can be expressed by these equations, and which can be related to water content and the pressure dependence, actuation volume, and temperature dependency. So this is at high fixed pressure and a different temperature, and water content fixed different temperature. From this, we can see the activation volumes, temperature dependency. So this is a result of the pressure dependency, so that in alpha beta transformation with containing some amount of water, pressure dependency is very weak. Temperature dependency is very high. And this is a water content dependency. This is a water content, and this is growth rate, so that we have very strong water content dependency. So we can get some parameter of this is effect water content dependency, activation energy, and activation volume. Based on this work, we can analyze the how the metastable living wedge can survive under the wet conditions. And this is the depth, and this is the transformed fraction. And ring that contains 5,000 ppm water, and this is 5,000. This is 500. And so in 5,000 ppm water, the transformation of alpha beta transformation complete at about 450 kilometer depth. So that eventually there is no metastable living wedge. But on the other hand, if water content is low, about 500 ppm, it can survive to 650 kilometer. We assume a bit lower temperature and the thermal gradient and subduction vertical speed is 12 centimeter per year. So that this is a remarkable result that the metastable living can survive at a depth greater than 650 in cold slabs, even in case of the water content less than 500 ppm. So that this is a very interesting observation, because in subducting slab, even if total amount of water is high, most of water can be absorbed by hydrous phases because of the phase relation. And therefore, very low water content in olivine and wozeliate can be achieved in existence of phase E under the lower temperature condition in subducting slabs. Therefore, this is a partial conclusion about this part of my talk. The water content in olivine, wozeliate, lingudite are relatively low when coexisting with hydrous phases. And hydrogen favors hydrous phases compared to olivine, wozeliate, and lingudite. And also that the hydration reaction occurs due to warming up the slab. And this could trigger the mantle seismicity. And this dehydration have a negative volume change. And also that sluggish alpha beta transformation can occur under the wet slab conditions. So that this, of course, contraction, volume change is negative. So metastable wedge is not the signature of a dry subduction. This is a very important conclusion in this talk. So we have some time remain. Seven, okay. So that this is the final topics. Then hydrogen, how hydrogen can move to the lower mantle. So that this is a subduction zone and the stagnant slab. And stagnant slab, after stagnant, sometimes collapse into the base of the tension zone. And we can see remnant of old subduction in the core mantle boundary regions as some cold anomalies. And this is the cartoon by Maruyama. This is super downwelling during supercontinent formations, so that large downwelling, cold downwelling exists beneath China and Japan areas. So that this kind of collapsing of the subducting materials can transport water effectively. In these processes, important mineral is delta phase and the phase H These are end member of aluminum end member, and phase H is magnesium silicate end member. And these are actually forms solid solution. So this solid solution is very important of water transport into the lower mantle. This is very interesting structure, which is similar to stishovite or CaCl2 structure of SiO2. So that is very stable and can be stable up to the base of the lower mantle. This is our experiment of the stability of this phase is pressure and temperature. This is a core mantle boundary. And this phase can be stable up to 134 GPa, 2000 Kelvin. So this can transport water into the deep lower mantle. And the very important point is the partitioning of water and aluminum between bridgemanite and these hydrous phases. And we made some measurement of the coexisting composition and determination of coexisting bridgemanite and this delta hydrous phase H solid solution. And the result is very impressive that bridgemanite contains very low amount of aluminum, and the bridgemanite is essentially dry. So water and aluminum move to this phase, so that under the wet conditions, hydrogen and aluminum can change different from the dry condition. So this is the composition between of the bridgemanite and delta H solid solution. And usually the bridgemanite contains very small amount of aluminum. This is 0.01, and this is 0.05. If you go higher pressure, it contains also 0.05, which is coexisting with post-perovskite phase. So that water and aluminum is coupling under the lower mantle conditions, and most of those water and aluminum can move to the hydrous minerals. So this is a cartoon that stagnant slabs move to the core mantle boundary regions, and this hydrous phase can transport water into the base of the lower mantle. So this is a summary, and mantle transition zone wet, and there is metastable leaping wedge even under the wet conditions, and hydration occurs several places in the mantle transition zone, and wet flow mantle can contain alumina depleted bridgemanite. Thank you for your attention.